Here's a student practice problem for which you should have all the information you need in order to do it yourself. I recommend trying this yourself before watching the video and then coming back to the video so that you can either check your answers or just watch to see wherever you got stuck or weren't sure what to do. So pause the video right now and give it a try if you haven't already, and then come back to it and unpause. The first thing we're asked to do is to check conditions for using a normal distribution for inference with this sample. So recall that for one proportion, what we want to verify is that what we're counting and what we're not counting are each at least 10. What we're counting is 76% of 418, and that we would calculate as 0.76 times 418. Now this comes out to be 317.68, which we'll say is about 318. Since we know it had to be a whole number of subjects responding this way anyway, it does make sense to round this to the nearest whole number. So most likely that 76% is rounded and that really 318 is the number of subjects who maintained their target weight loss 6 years after surgery. As for what we're not counting, there's usually two ways to get that number. One way is to look at the fact that there's 418 total in our sample and 318 are what we're counting, so that leaves 100 as the other number. But if we follow the formulas that we saw for checking conditions, then that will also work. That would be n times 1 minus p. We really already did n times p hat. It's really p hat times n, the way we wrote it here. And then if we wanted to do 1 minus p hat times n, then what that would look like is 0.24 times 418, which comes out to be 100.32, and we can see that yes, that one also would round to 100. Now in checking conditions, we need to verify that these are both at least 10. And we need to say that conditions are met because these numbers are both at least 10. Yes, conditions are met. Now here's a really important point. When we are answering a question about checking conditions on a homework or a test, I expect to see all of these so that I can be convinced that it wasn't just sort of a guess, right? Yes versus no, you got a 50% chance of getting it right. And in fact, the answer is yes more often than it's no if we're asking you to do the inference, so you have a better than 50% chance of getting it right if you say yes. But you're not going to get credit for an answer like this unless you show what numbers you had to calculate in order to answer it, indicate what you had to compare those numbers to, and remember to actually answer the question. Don't assume that that yes is implied just because you said both of these numbers are greater than or equal to 10. All right, we need to show the calculations. I mean, you don't have to show all of this, right? But you have to show what numbers you calculated, state that 10 is the number you're comparing them to, and answer the question with a yes or a no. Okay, so conditions are met. Now we'll go ahead and find that 99% confidence interval. We are going to need a z star. We're going to need a standard error for which we have a formula. And once we have both of those calculated, we'll be able to calculate our margin of error by multiplying them together. Remember that z star is just a table lookup. We have a 99% confidence interval, and z star only depends on the confidence level. So our z star is 2.576. For our standard error, we know that our sample proportion p hat is 76% or 0.76. 1 minus p hat is 0.24. And n is 418, and the whole thing is inside 1 square root. So putting that into a calculator gives us 0.0212976. Since I want to take my standard error always to at least 4 decimal places, I'm going to make an adjustment. The next digit is a 9, which is greater than 5, so I will round this up to a 3. So 0.0213 is my standard error estimate. And now my margin of error is equal to z star times the standard error, which is 2.576 multiplied by 0.0213. Again, remembering that the number of digits to take this margin of error to is often either to match the number of digits of your sample statistic or take it 1 decimal place farther. Since this is a kind of small number, I'll go ahead and take it 1 decimal place farther to 0.055 when I have rounded that appropriately, so that my confidence interval is p hat plus or minus the margin of error, which is going to be 0.76 plus or minus 0.055, and I will now subtract to get the lower bound and add to get the upper bound. So for my final interval, I get from 0.705 to 0.815. Now to interpret the confidence interval, I have to think about the context. So we're talking about the proportion of subjects of all those who received gastric bypass surgery, the proportion who maintained a target weight loss 6 years after surgery. So we know that that proportion is in this interval, meaning it's between these two values. We want to now say that in context. With proportions, I often like to word this in a slightly different order from how I would word it if it were a mean. I can say the proportion is between these two values, but sometimes it's more clear to convert them to percent and to put the percent first before defining what that percent really is. So for example, I'm going to start out this statement by saying with 99% confidence between 70.5% and 81.5% of, now I need to define the population and what we're counting and make it into a statement that makes sense. All gastric bypass patients is my population, so that comes next. So between 70.5% and 81.5% of all gastric bypass patients. And now what we're counting is those who maintained their weight loss 6 years after surgery. All right, so we're following the general model for a proportion of the population that, and then we indicate what it is that we are counting. Now finally, we have the question of what method could you use for a confidence interval if conditions were not met for a normal distribution. This is where we want to reflect back on the fact that we were doing confidence intervals before we ever saw normal distributions, and we were using a bootstrap distribution for those. So we would say a bootstrap distribution for one proportion And in particular, if we think about that for a moment, there were some confidence intervals that we did using bootstrap distributions where we said we had to assume that the bootstrap distribution was approximately bell-shaped, and there were some for which we did not have that assumption. The kind where we did not have that assumption were the ones that we used the percentiles method on. The other method that we used with bootstrap distributions was that margin of error equals 2 times the standard error. That's actually based on the normal distribution theory, even though we hadn't really seen that yet at that point. And remember that there was an assumption in there that our bootstrap distribution was approximately bell-shaped in order to use this formula. So we don't actually use that approach, but the percentiles method does not assume a bell-shaped distribution of any sort. It still works for the most part under any conditions.